Hello and welcome to this session on configuration, design and implementation of a microprocessor-based system. Microprocessors and microcomputers are used in a variety of applications. Some representative examples are washing machines, process controllers, programmable instruments, modems, and CNC machines. Designing any of these instruments, or for that matter any other microprocessor-based instrument, we follow the same steps. We start with drawing up our specification of the system, then we examine the implementation strategies. We'll also look at various design alternatives available to us. Once the system design is complete and it is thoroughly implemented, we go for test and debug procedures. So, what do we expect from the designer when we say that he has to design a microprocessor-based system? The designer should understand the hardware components of the system and also the software processes involved. Further, he should be able to integrate these two requirements so that the system performance specifications are met. Now, what do we mean by hardware components? As you have guessed correctly, the hardware components include the microprocessor chip, the memory chips, and the I/O chips. These constitute the microcomputer. Further, we will need the transducers to sense the inputs, actuators to control the process. Further, we need keyboards and switches to set up the instrument. Also, we require displays to inform the user about the results. Now, what is a software process? Let us consider an example where a relay is to be switched on for a fixed amount of time. During the interval, the microprocessor will send a logic 1 onto a specific port. After the interval is over, the microprocessor will send a logic 0 onto the same port. So, the software requirement of this process is a delay interval. We should be able to identify such requirements on the part of the microprocessor, and then we should be able to translate these software requirements into a sequence of instructions which the microprocessor can understand. Finally, we should be able to integrate the software and hardware requirements of the system. This is a very important component of the system design, and so we should go into this in greater detail. We have identified the hardware components and the software processes required for the system. Now, we have to integrate these two. Let us take an example to describe the integration process. In this particular example, there is a keyboard, and in the software we have a delay subroutine. This software delay subroutine is doing the job of key debouncing. We can now describe the underlying guidelines for splitting the design into interconnected modular subsystems. The design guidelines are: interrelated parts of the system stay together, unrelated parts of the system do not stay together. This way, we can specify, design, implement, test, and document complex systems. Let us illustrate the above idea with an example. Consider a microprocessor-based temperature controller. At global level, we look at a black box which is called the microprocessor. We open this box, we look at the transducer, microprocessor and display. When we open up the transducer box, we look at the temperature transducer, its signal conditioning circuitry, interfacing to an AD converter, interfacing of AD converter to the microprocessor. Further details can be obtained by considering the temperature transducer alone. What is the type of transducer being used? How it is connected to the remaining portion of the circuit? Does it use 2-wire, 3-wire or 4-wire connection? This way, by looking at sub-functions of the system, we gather a large amount of information about the system. This type of splitting the design into sub-modules is known as top-down design methodology. Let us consider a microprocessor-based temperature controller to describe the steps involved in the design process. The first question that comes up to our mind is, what are the features of this system? They are: system should directly interface with the transducer, online display of temperature, and output of the system is relay changeover of contacts that switches a heater on or off. The next question that comes up is, what are the performance specifications of the system? In our example, they are: the temperature range is 0 to 600 degrees centigrade. The control is within plus minus 1 degree centigrade, and the relay should be able to withstand 5 amperes of current. How does the operator interact with such system? In our temperature controller example, operator selects the set point temperature and also he specifies the maximum temperature above which the process should shut down. How will the system interact with its environment? This can include such details as handshaking and control, voltage levels, etc. In this example under consideration, the same are: the system uses a sensor to sense the temperature of the process and it switches the heater on or off using the relay. How will the system provide us with a hint that something is faulty? And also, should an operator interact with the system in order to remove the fault, or will the system remove the fault on its own? So, in our example, the provision is: the system restarts after a power failure without operator intervention. So, we can use thumb wheel switches to sense the input temperature that is set by the operator. Can you guess how this power failure emergency is met on your microprocessor kit? Another system error feature that is introduced in our system is: if the sensor fails, blank the display. This makes it easy to locate the problem in our system. The next question that comes up to our mind is: can we select a component at random, or is there any constraint on the type of component that we are going to select? These are called the design constraints. Some design constraints are power consumption, operating temperature range, corrosive effects, and physical dimensions. In our example, the design constraints are: ambient temperature range is 10 degrees to 50 degrees centigrade, operation is on 230 volts AC, and the panel size is 192 millimeter by 96 millimeters. So far, we have covered the requirements definition for our system. In this, we have discussed what are the desired features of the system, how the operator is going to interact with the system, how the system is going to interact with its environment, how the faults are diagnosed, and also what are the design constraints. Now, in this example of microprocessor-based temperature controller, the microprocessor-based temperature controller is an improved version of analog controllers. So, we are quite thorough in the design features, also the technical specifications. But let us take an example like a washing machine. Washing machine is a household appliance and it is going to be used by non-technical persons. So, in such cases, the designer would like to include safety as a major criteria. Further, he would like to reduce the user interface and simplify it as much as possible. So, before we embark on the design process, we have to develop an understanding about who is going to operate the system, where it is going to be operated, and what are the operational environment. This is called the context analysis. Context analysis is not really necessary in all design processes. It is required only in innovative and altogether new microprocessor-based system designs. So far, we have defined the system requirements. Now, how do we realize the system with these requirements? For this, we split the design into small, interconnected modular subsystems. What is the basis for this splitting of the system into small pieces? The golden rule is to partition the system such that we get submodules which have minimum interface. In the example system we have been dealing, this corresponds to having the circuit blocks arranged in this way. The number of signals from any given circuit block is kept as minimum as possible. The thermocouple output sensitivity is of the order of 50 microvolts per degree centigrade. This voltage is too small to be processed. We need to insert some gain stages before the signal is fed to the AD converter. The required gain depends on the total dynamic range of the input signal. Depending on the maximum and minimum temperature of the input, we may need 10 or 12-bit AD converter. The corresponding software flowchart would appear in this way. After linearizing the input from thermocouple, the system makes a comparison between the set temperature and the thermocouple output. If the process temperature is more than the set value, the relay is switched off. If the process temperature is less than set value, then the relay is switched on. If the need arises, it will sound the alarms and may also change the LED status. The system also displays the temperature of the process. For this, we need a port line and multiplexing mechanism in order to conserve the total power consumed. Since all the inputs and outputs are I/O mapped, we need to have programmable peripheral interfaces and I/O decoding logic. The next task in our systematic design is selection of an overall implementation method. We have two possibilities here. One is non-programmed logic method. The other is programmed logic method. Non-programmed logic method is used for systems of low complexity. We have the famous TTL 74 series implementation which comes under non-programmed logic method. Programmed logic method means that the integrated circuit is not coming under a same package. We are programming the logic. Since in our example the system is not very complex, we can use the non-programmed logic method. The next task in our system design is selection of the microprocessor itself. The selection criteria is normally the software features of the microprocessor, the hardware features of the microprocessor, and the support. Since the system that we are going to design is not very complex, and also there are not many data manipulations involved, so we will use the famous 8085 microprocessor itself. How do we decide that a certain portion of our design should be implemented by software or certain portion of our design should be implemented by hardware? Let us take the example of our temperature controller. Here we have a transducer which is highly nonlinear. There are two options with us. One is to have user programmable gain stages. The other is to have a RAM lookup table. If we are using the RAM lookup table, then naturally we are looking for a software solution. Similarly, we may have the AD converter control signals polled by the microprocessor, or the AD converter can interrupt the processor when the data is ready. By interrupting the processor only when the data is ready, we are saving the microprocessor from keeping on polling the I/O device. So we are opting for a solution where a certain amount of software is saved. Let us take another example to understand the division of tasks between hardware and software modules. Let us consider a 4x4 key matrix being used to enter commands and data into the microcomputer. We can recognize a key being pressed by using two 4-bit ports. A logic 0 is passed on each output port line sequentially, and the status on the input port is read. This way, in and out ports can be used to identify a key being pressed. The software requirements for the keyboard interfacing are: output a code and read input port, eliminate key debouncing, forbid any other key being pressed, and do all these operations in a loop. These tasks will load the microprocessor sufficiently. But let us consider a situation where the processor has to do some other data manipulations, or it has to do some other I/O operations. Then it may not be possible for the same processor to do all these jobs and in real time. Then what is the alternative solution? We can delegate all these operations that are previously done by the microprocessor to a peripheral device. In this case, it would be a keyboard controller. It is possible to hand over all these jobs to a keyboard controller chip so that the processor is free to do other essential jobs. Here, a large portion of software is traded off for a few extra hardware components in order to boost the system performance. When do we go for a trade-off? Usually, we go for a trade-off to increase the performance of the system and reduce the cost. How to describe the speed of performance of the microprocessor? We can describe it in terms of the I/O execution speed and also by the data manipulation speed. In case the data manipulations are not carried out in sufficient time, then we may have to go for a faster version of the same microprocessor, or even we may have to go for the read-write memories which have little access time. So far, we have discussed the systematic design phase. In this phase, we discussed how to partition the system into easy to implement circuit blocks, decided about the overall implementation method, selected the microprocessor that suits the application and decided about the hardware and software trade-offs. The next task in our systematic design procedure is the system implementation. We have two alternatives available to us. One is using prefabricated boards. The other is using the chip-level design. Chip-level design results in system which is very compact, but the time it takes to design at chip level would be quite big. Likewise, using prefabricated boards will result in system designs which have many unnecessary components, but it is very easy to do the design process. Testing and debugging of the system is our next stage in our design methodology. Testing of the system helps in finding out whether the system has any errors. Debugging helps in locating these errors and eliminating them. The best way to test the system is to break the system into small circuit blocks. Then these relatively independent circuit blocks are tested, and then such relatively independent circuit blocks which are successfully tested are cascaded, and again such cascaded circuit blocks are tested. Let us consider an example to describe this. Interfacing the microprocessor with read-only and read-write chips is one functional module. Now, we write a small program that does nothing but simply loops back after writing a byte in the RAM. We will read back the byte to verify whether the data bus is properly connected or not. The result is displayed on the serial output data line SOD. We start the testing process by checking all the PCB tracks and find out whether they are properly connected to all correct IC pins. Once the processor starts executing the code, we can verify power supply on each chip, the ground voltage on each chip, the chip select signals on read-write and read-only chips, the read-write control signals on each chip. If we find that any of these signals are not proper, then we can trace back the circuit up to the processor itself. This way, it becomes easy for us to correct the design problems. This method of debugging is called bottom-up approach. The advantages of this testing method are quick localization of the problem, ease of testing, and use of a few test instruments. Further, we can test the software subroutine by subroutine along with the hardware functional module tests, and in this way we can complete the software test also besides completing the hardware test. While testing the software, we test all conditional jumps to test every decision statement in the program. Eventually, we carry out the system test to see whether the system is meeting the performance specifications that we have drawn up at the beginning. This can be carried out by placing the thermocouple in a hot water container and verifying the state of the relay. Finally, we should take care of the software and hardware maintenance and documentation. Hardware maintenance would mean correcting design errors and component failures. Software maintenance would mean correcting software errors and upgrading the software to improve the system performance. This can be done successfully only when we have the system details in a well-documented form. The document should be comprehensive and unambiguous. In this session, we have taken up the problem of designing a microprocessor-based temperature controller. We first identified the requirements of the system. Then we partitioned the problem, identified the microprocessor that is to be used, and decided about what design aspect should be implemented by hardware and what design aspect should be implemented in software. Then we decided about whether we should use prefabricated board or we should start the design from basic chips. In order to reduce the overall cost of the system and fit it in a given volume, we decided in favor of design using basic chips. Then we discussed the test and debug procedures that helped us identify any remaining design and PCB problems. Finally, we emphasized the need for good documentation. It is hoped now that we will be able to configure, design, and implement a microprocessor-based system.